Now like that, because him and I gone. That was because we're no longer friends. He's the one that made me do that. And I don't fire shoes or orders because he just doesn't jump off the floor even though it's not him. Off the city streets. Saying it's his when it's not. And I sat in here that somehow. Oh yeah. Great, good. You go to jail in the future. No, if he does that to the wrong person, like he to the wrong person, and that could turn him in, and he could get nailed in the butt in the future. So this is the best bet my friend told me to do during 4,000 PCM and give it to him. See his reaction. You might be mad at me, but I don't care. I don't care if he gets mad at me. I don't care. I see him 3 times in a row. For real. You haven't done it. It's not your fault.
Good morning, ladies and gentlemen. How are we doing today? Why? What's wrong? Tell me all your problems. I got 30 seconds. Go. Good. Wonderful. Excellent. Thank you for sharing. All right, ladies and gentlemen, grab your computers, get logged in, and go to joinpd.com. What? Well, it's not about want, it's about need. You need to. Yo!
How many days do we have left to school?
Until the end. I don't know. Count them. I have no idea.
Hold on. I had an email that it was like.
And then 2
I had an email with something about. Hold on. I have that email.
You meant, no.
my one quarter girl was like, yeah, we only got 2 weeks. And I'm like, I was told 5 weeks. What do you get 2 weeks?
So,
5 weeks for what?
we have 15 days left to school. 15.
Okay.
I think it's
From yesterday, we had 15.
Okay.
And only 11 for the seniors.
Zoe, we got it. Thank you. We got it. All right. All right, ladies and gentlemen, and your computers, if you would go to joinpd.com. We got a little pear deck for you, ladies and gentlemen, and here is your code. WTQPNZ.
Warm turnips quietly pursue new zebra.
You just can't type in the letters
No, he's got to read it.
every time.
So do
I have to
I.
read it.
You don't have to read it out loud.
I have to read it too.
Again, read it. Don't read it out loud. Other
That's
people will
fun.
find. What?
I said it's not as fun though. It's fun reading it out loud. And it's about it.
Okay. All right.
Exactly.
So
Mr. Brand, you have to go to Canvas next year too.
Yes.
Apparently, all teachers are going to Canvas next year. Yes.
So in school, we have to go to campus. It
Okay.
sucks.
Zoe,
I don't like it already.
You
why?
don't have to comment.
Because I have it in PFL
So what's wrong with it?
because I don't like it because all your assignments in the modules.
Okay, your assignments
you
are in
have to-
Google
you have-
Classroom in
I
Classroom.
know, but you have to. If you have an error on the assignment, you have to resubmit it fully, or to resubmit the whole assignment fully again. Instead of like unsubmitting it like Google Classroom and resubmitting it, you have to like make a new attempt on the Canvas, and you're
Okay.
time limited on tests.
And you could be time limited on tests in Google Classroom. That depends on if the teacher wants them to. Aren't you time limited on mine? Don't you have to be done before the end of the hour?
True, but certain
Okay.
teachers have like certain exceptions.
Every teacher is a little bit different, so.
And I heard bad things about
It'll-
Canvas, certain
Okay.
things.
Okay. I've heard good things about Canvas. I've heard bad things about Canvas. It'll be okay. It'll be something new that we will be getting used to. So, all right. So get logged in, the last couple people here, please, ladies and gentlemen, so that then we can get this going. But yes, all teachers are supposed to go to Canvas next year.
Why is that? Because of the subscription?
The district decided to use Canvas instead of Google. I don't know exactly why. They say it's partially because that's what a lot of colleges are using. But again, I don't know for sure.
Do you
Gonna
like
be
Canvas
a-
more than
oh.
Classroom?
What's it?
Do you like Canvas more than Google Classroom?
I don't really care.
All
Let's
I
put it.
know is all your assignments are in the module section.
Okay, but Zoe, all your assignments have got to be somewhere. They call it modules. In Google Classroom, they call it the classwork page. It's the same thing. Because literally, for teachers, we had to take a class. And it's like, here it is in Google, here it is in Canvas. Yes, they call it different things. You're absolutely correct, Zoe. But the assignments just go somewhere like before. A lot of assignments could still be done in Google as well. So you can assign Google assignments through Canvas.
Like you would have to attach a file of everything.
Zoe, relax,
I do it in
okay?
PFL.
I understand, Zoe, but you've made your point perfectly clear, Zoe. We beat this horse to death. Let's stop, okay? Okay. All right. So here's the one thing. This is the only thing, Alex, that I personally was upset about. I'm teaching chemistry for the first time this year in a lot of years. I hadn't done it before. So I emailed the people downtown and said, well, if I'm going to reset up a chemistry class, are we going to Canvas soon? Because if we are, I'll do it in Canvas. Oh, no, you got time. Don't worry about it. And then during the year, they decided, yes, we're going to it. So I had set up my class in Google Classroom. I guess it isn't that hard. But again, it'll be something new. It'll be something different that we'll all be getting used to. The one nice thing I like about Canvas that Google Classroom doesn't do as a teacher, I can click on and see what you guys see. So the way you see things on Google Classroom is not the same as the way I see them on Google Classroom. But in Canvas, I can click on it and I can see how you guys will see things. So that if I need to show you something, I can click on what your view of it will be and show it to you. That's kind of nice.
That's a grand. When are we starting school next year?
We are starting on August 26th. Okay? So that is 1 week earlier than we would normally start. And again, we'll start with an asynchronous day for the upperclassmen, where only the freshmen are in school. And then we will have class Tuesday, Wednesday, Thursday, and you guys will be off Friday and the next Monday. That's Labor Day. So you guys will have a 4-day weekend right away. So they are starting earlier. We don't get out any earlier. And the day is 5 minutes longer next year. So you will get out at 3:05, not 3 o'clock.
Because they added 5 minutes to home base.
Stupid.
You are correct. They added 5 minutes to home base for next year.
What? That's dumb.
I completely and totally
That's so
agree with you.
dumb.
It is the least attended hour of the day, and that is the one that they put the extra 5 minutes on. But all we could have done here would have been to add 1 more minute to each class.
That would have been smarter.
I understand that, but because the other schools are on a different schedule than us, they chose just to add it to home base. So
Also, all schools got an extra 5 minutes.
yes, every school in the district got an extra 5 minutes.
So instead of my brother getting out at 3:30, he's getting out at 3:35.
Again, I know the high schools are extending their day 5 minutes. I don't know if other schools are maybe going to start 5 minutes earlier. I don't know. I can't tell you for sure. All I know is our schedule for next year, and that is home base is 5 minutes longer. Your day ends at 3:05. You won't even notice it. You won't. Okay? But again, I agree with you guys. I don't know why they would put it in home base when it's the least attended hour in the district for students. Yes.
You know what they should have done? Just
What
put-
should they have done?
Just put 5 extra minutes for lunch. I feel like that could have been.
They couldn't.
What?
Well, we have 2 lunch hours.
If one gets
If one gets 5 minutes, the other one gets shorted 5 minutes. You can't split it up 2.5. And what you have to remember is while that lunch hour is happening, there's a class in session. So that class would get longer. So they didn't want to make one class longer than the other classes. That doesn't make sense. So instead they chose to add 5 minutes to home base. Now, in reality, what it does for us is it gives us more minutes throughout the year, which means if we have more snow days and things, we don't have to make them up. That's really what it means. It gives us more cushion, basically. Because 5 minutes a day over 180 days, that's quite a bit extra time.
But how I think about it is, for me, is homeroom's just like another studio. Get what you need to get done.
So then why wouldn't you want 5 more minutes in your study hall?
Because it's already long enough.
Until teachers get bullying.
Again, I wish I could help you with these things, guys, but these are decisions that are far above my pay grade. And they very rarely ask me my input because I will exactly tell them what I think. So,
We need people more like you.
no, the district disagrees with you very much on that. Today, ladies and gentlemen, we're going to learn about properties of metals and nonmetals. Yesterday, we did our activity where we talked about the reactivity of different metals. Today, we're going to try to put that together with some other properties about things and stuff like that. Okay? Again, a couple of reminders, ladies and gentlemen. Most of you did pretty well on the last test. You don't have to worry about a retake. But if you got in the 60s or lower on the last test and you want to do a retake, you have until next week, Thursday, to do it. Again, not a lot of you. None of you have any missing quizzes, so that you're good on, or tests. But if you're missing a lab, you got till next week, Thursday, to get it turned in. And there will be a quiz this week, Friday, in 2 days. Tomorrow I'll put out a Quizlet for you to review. Periodic table trends, the ones that we talked about yesterday. The types of elements, in other words, what we were also talking about yesterday. Is it a metal? Is it a non-metal? Is it a metalloid? Things like that. And then the periodic table. So we'll do a little bit of reviewing there as well, ladies and gentlemen. Okay? So here we go, ladies and gentlemen. Here's our first question. What happens to the number of valence electrons as you go across the periodic table? Does it increase? Does it decrease? Does it stay constant? Or is there no pattern to it? So the number of valence electrons as you go across the periodic table. And please remember, for a lot of this unit, for a good portion of this unit, ladies and gentlemen, we are ignoring this area of the periodic table in here. And it is not that that is not an important area, but that area doesn't fit a lot of the patterns that we are trying to establish in things. So just keep that in mind. So what happens to the valence electrons as you go across the period? If you would, please, too, ladies and gentlemen, please put away your phones and your electronics other than your computer. Okay? Thank you. So slide your icon, ladies and gentlemen, and let's see what we get here. All right, let's see if everybody can line them up right on top of one another. Hey, very good, ladies and gentlemen. Absolutely everybody is correct. It increases. So as we go across the periodic table, the number of valence electrons increases. We start out with 1, and what number do we end up at? What is our maximum? 8. 8 is the maximum. Very good. Okay. What happens to the atomic radius as you go across the periodic table? So now the size of the atom. What happens to it as you go across the periodic table? Again, the same 4 choices. increases, decreases, stays constant. There is no pattern. Not as many confident choices as last time, ladies and gentlemen. A little bit more spread out. Okay, that's fine. Let's make sure we understand this. It actually decreases as you...
My first idea was right.
Okay, Zoe. Okay. It decreases as you go across the periodic table, ladies and gentlemen. It gets smaller. And again, the only explanation that scientists can give for this is there are more protons in the nucleus, and that pulls all the electrons a little bit closer to it. Okay? All right. What happens to the atomic number as you go across the periodic table? What happens to the atomic number as you go across the periodic table? Okay? Since the atomic number is unique to every element, ladies and gentlemen, it cannot stay constant. Cannot. It increases. By the way, all you got to do is look at the periodic table, ladies and gentlemen. Look at the numbers as we're talking about them going across. Atomic number is right above the element. Should not be a problem, ladies and gentlemen. Okay? All right. What happens to the number of valence electrons as you go down the family on the periodic table? So now we're not going across, now we're going down the family. What would happen to the valence electrons? Hello, a minute. Okay? As you go down the periodic table, ladies and gentlemen, the valence electrons stay constant. They do not change. Okay? That is a trend of a family, so they do not change, ladies and gentlemen. What happens to the atomic radius as you go down the periodic table? So again, remember, we did all these trends going across. Now we're doing them going down because they can change as you're going down the periodic table instead of across. So what happens to the atomic radius of an atom as you go down? And by the way, you should have this on your periodic table. So again, if you don't have it out, that's fine. But yesterday, we asked you to write these on the side and on the bottom of your periodic table so that you had them in one location. Okay? As you go down a family, the atomic radius increases, ladies and gentlemen. It gets bigger and bigger and bigger as you go down. Questions? Okay. What happens to the atomic number as you go down the periodic table? Better here, ladies and gentlemen, it increases. It increases. As you go down the periodic table, the atomic number increases. Questions? All right, take out your periodic tables, ladies and gentlemen. Get them out on your desk for what we are going to be doing next, ladies and gentlemen. Yes, Jess.
Old people at work are mean.
Old people at work are mean. Well, we just get more and more bitter as we get older. You'll get there someday, Jess.
I hope I don't.
I hope you don't either. But I never thought I would, and I yell at kids all the time to get off my lawn now. So.
You're one of them old people, Mr. Brown.
No, I'm actually not. Why? There are no kids where I live. So. All right. So as we look at this periodic table, ladies and gentlemen, and as you look at yours that you have out, please take out your periodic table. Ethan! Okay, please remember, what are the numbers on the side tell us?
The period.
The period. 1 through 7, ladies and gentlemen. What are the numbers on the top tell us? The what? The family or the group number. Technically, it's the group number because the family would be a name. But, okay, I'll take it either way. Main thing, we know the elements are going up and down, right? All right. Period 4, group 16. What element is it? Period 4, group 16. What element is it?
Selenium.
Okay. Period 4, group 16, selenium. Very good. SC. Period 2, group 2. What element is it?
William.
Beryllium. Right here. So if you ever played the game Battleship when you were a kid, where you call out A7, oh, miss. B6, hit. That's what we're kind of doing here. So every element on the periodic table, you could find it by knowing its period and its group number. There is an exception to this, though, ladies and gentlemen. Anyone know what the exception is?
The bottom ones like go 6 and 7.
Very good, Zoe. These bottom ones down here,
And also 6 and 7.
they are in period 6 and 7, but they are not in a particular group of the periodic table, just so you know. So you can't find this one by going period 6, group something, because there is no group for it. Okay? But all of the other elements, you could find them. Period 5, group 7. Period 5, group 7. What element is it?
What?
Period 5, group 7. Give me the symbol.
PC.
TC. Tactinium. Okay? So again, ladies and gentlemen, we can find any element on the periodic table by knowing its location and, or basically, period and group number. Questions? Okay. So, yesterday, ladies and gentlemen, we looked at 5 different elements. Actually, we looked at more than that when we count the video that we looked at. The elements that we looked at yesterday, ladies and gentlemen, were as follows. So I'm going to highlight them on here for you. You do not need to highlight these on your periodic table. I'm just doing it. This, oops. This was the first one. Second, then we looked at lithium, sodium, potassium, and these 2 down here, rubidium and cesium, these were on the video that we watched. Okay? So we showed you 5 out of these 7, and then we showed you these 2. Now, what do we know about the reaction for magnesium? Of all of the reactions, how would you describe it?
It color.
Well, they all turn color.
I know it changed like the metal color.
They all changed colors. What do you, yes, okay. I guess, thank you. I should have asked the question better, Alex. That's kind of what I was looking for. Out of all the reactions that we did, magnesium was the worst. Absolute worst, right? Reacted really slow, very little color change. It happened down by the metals. Oh, you were right, where the metal was. Not a lot happened here. When we did calcium, it did get a little bit better, right? But again, there was no bubbling. There was no, it just turned a little bit pinkish color. Okay? Then when we slid over and then when we did lithium, lithium actually looked like a reaction. Why? What did it do that none of the others did before that magnesium and calcium didn't do? It popped.
It bubbles.
It bubbled, sparks, all those kind of things were happening.
It flamed.
Turned a large amount of water to a darker red color than calcium or magnesium, right? There weren't any flames yet. There weren't any flames. But then we slid down one more and we got to sodium. Sodium, reacted as well. But with sodium, what happened that didn't happen with lithium? It did catch on fire. Okay? It burnt. What was actually burning? The metal was not burning. Let's get that clear. What was actually burning? Nope, water doesn't burn.
I may be wrong, but the fiber in the middle.
Nope. Nope. What? Energy was given off, but energy did not cause the burning. Something has to burn. If you're going to have fire, something has to be burning, correct? What was it?
The chemicals in the middle.
Nope. The metals were just one thing. The metal was just lithium, just sodium, just potassium. But there was a reaction, right?
Mm-hmm.
And describe what happened in the reaction in the container. And don't tell me it burned. Tell me what other things happened.
Space screen.
What? Smoke. A gas was released. What gas?
Hydrogen.
What burned? Thank you. The hydrogen gas that was given off. Now, with lithium above sodium, the hydrogen gas was given off as well. But let's go back to what Faith said. Faith said what was given off? Energy. And with the lithium, there was not enough energy given off, ladies and gentlemen, to actually catch the hydrogen on fire. It was not strong enough or enough energy to where it could make it start burning. But with the sodium metal, it was. There was even more energy given off than there was with lithium, and that actually caused the hydrogen gas that was given off to burn. Okay? When we slid down to potassium, what happened? That little chunk of potassium, what happened? Right? Okay. While it was a smaller piece, this never caught on fire. This took a few seconds to caught on fire. This, as soon as it hit the water, was on fire. Meaning it was releasing the most energy out of all of them. Okay? It didn't seem as good as this one because this was a much larger piece of sodium than this was of potassium. That is just the way it was, ladies and gentlemen. Just the way it was. Okay? Point being, though, ladies and gentlemen, as we are moving down here, what's happening to the reaction? It's getting what? Bigger, stronger, more reactive, however you want to say it. Then, ladies and gentlemen, I told you, they won't give me cesium, they won't give me rubidium. I wish they would, but they will not. Okay? But as we move down in the video to cesium and rubidium, what happened? This one exploded as soon as it hit the water, and this one blew the side out of the container. So what we are obviously seeing is that as we go down here, what happens to the reactivity? Gets stronger. How does magnesium compare to sodium, though? Magnesium's reaction compared to sodium's?
I want to say the same thing with the milk.
They're not. Now they're next to each other. Which of these two is more reactive? Remember, the magnesium is the very first one we did. Sodium was the one that blew up and scared out of Faith.
And me too, partly.
Which one is more reactive? Come on, where did I do the first reaction?
The second one.
Where did I do the first reaction? On the table in front of you. Why? Wasn't as reactive. Now, this reacted with water, correct? This reacted with water, correct? Okay, the next element over is this one, right? Aluminum. What is the main ingredient in soda?
Water.
No, the main ingredient.
Sugar.
What?
Water.
Water. Now there's a lot of sugar. There's a lot of corn syrup. There is carbonation, but the main ingredient in here is water, which is now in what kind of can? Aluminum. Are they reacting? Are they?
Could explode your hand right away, right?
When was the last time you saw an aluminum can explode in somebody's hand? From the soda inside it.
No, but like,
When you're done drinking a can of soda before you recycle it, you're supposed to do what with it? Supposed to.
Crush it.
No.
Rinse it out.
Rinse it out. Rinse it out, right? What are you putting in here? Water. Is there any reaction at all between aluminum and water?
No.
No. So, very reactive, slightly reactive, not reactive. Right? So as we go this way, what happens to the reactivity of metals?
It decreases.
It becomes a lot less. It decreases. Okay? So that is a trend going across a period. How about going down a family?
It increases.
This is less reactive than this, right?
Oh, so it decreases.
No. This is less reactive.
Oh, so it would increase.
Yes, I'm agreeing with you. These two, which one was more reactive? No. I'm over here. Magnesium or calcium?
Calcium.
Calcium. If I had strontium, do you think it would have reacted? More or less than calcium?
More.
We're seeing a pattern here, correct? We are seeing a pattern here. Good, ladies and gentlemen, good. Because we are going to talk about that today. All right. Next slide, ladies and gentlemen. All of the samples that we showed you yesterday were metals. So let's talk about properties of a metal, ladies and gentlemen. Here are some physical properties. Now, again, remind me, what's a physical property? Well, did you hear or see the reactions that were happening yesterday? Okay, so that's not the greatest definition. I agree with you. It is things that you can see and things like that. But to be physical, they are properties that can be observed without doing what to the substance? Thank you. That's the term we're looking for, without changing it. So if I put that chunk of metal on a balance, I can find its mass, correct? Does that change the metal? No. Throwing it in water, did it change the metal? No? The metal stayed the same after I threw it in water yesterday? Okay. So, physical property is things have luster. Any idea what luster is, ladies and gentlemen?
that's the shiny part.
Luster means it's shiny. Luster means shiny. So it's not only important that you write down it has luster, but you may want to put down what luster means. Luster means that it is shiny, ladies and gentlemen. Okay? Luster means that it is shiny. They are what is called malleable. What does malleable mean? What do you mean changeable? Because you're kind of right, but I need you to be a little more specific. What? Thank you. Malleable means it can be pounded in a sheet. It can be shaped. So, kind of what you were trying to describe, but you just didn't get it quite good with the words you were using, Ethan. So, in other words, you can take and you can make it into a certain shape. You can make it into a thin sheet. That is what malleable means. They have a high density. Most metals have a high density. What that means is there is a lot of atoms packed into a very small amount of space. Lead, very dense. Mercury, very dense. Iron, gold, silver, all very dense materials. A lot of things packed into a little space. Okay? So that is a property. Okay? Most of them are solids at room temperature. There is only one that is not. Which one? No, bromine's not a metal. Mercury. Mercury is not. They conduct, ladies and gentlemen. Now, what does it mean to conduct?
Reactive.
No, not reactive. What?
They take the energy away.
Okay. Conduct means that they will allow things to move through them. Now, what are the two major things that metals conduct? Electricity and heat. They conduct both heat and electricity. Okay? So that is why we use metals for pans. That is why we use metal for wiring. Because they will conduct heat and electricity very well. Okay? Now they have some chemical properties. Oh, by the way, we should add this physical property. They are ductile. Okay? They are ductile. D-U-C-T-I-L-E. D-U-C-T-I-L-E.
Which one?
For physical properties. Sorry. For physical properties, they are ductile. D-U-C-T-I-L-E. They are ductile. What does ductile mean? Ductile means that metals can be made into wires. They can be pulled out, they can be drawn into wires. Okay? That is the properties of a metal. At least the physical properties. Now, there are some other properties as well, but these are just the main ones. Now, guys, you do this every day. You come in, you start talking, you disturb my class. If it happens again today, you will be separated, and that will be a permanent issue. Okay? In other words, you will not be sitting next to each other. Okay? Thank you. Okay? So, is every metal shiny?
No.
No. Lead is not a real shiny metal. Okay? But these are the general properties of most metals. Gold, shiny. Silver, shiny. Titanium, shiny. Aluminum, shiny. But not every metal is shiny. Iron is not really shiny. Okay? So, but understand these are the general properties. All right, now, some chemical properties. What is it? If a physical property can be observed without changing the substance, what is a chemical property? It describes how matter will change. How it can become something different. Okay. Chemical property of metals is that they lose electrons. They want to give them away. They are trying to. And that goes back to that, okay, how many valence electrons do you have? How many do you need to lose to become stable? All of that stuff that we talked about in earlier units. But metals lose electrons. They form what is called a positive ion. Positive means it has more protons than electrons. Why? Because if you're losing electrons, you're going to end up becoming positively charged. Okay? And metals all make positive ions. That is what they always make. Okay? Metals react with these things. Now, again, the metals that we showed you yesterday, what did they all react with? Water. Does aluminum react with water?
No.
So again, not every metal will do these reactions, but in general, metals will react with water. Metals will react with oxygen. What do we call that? Rusting if it's iron. If it's copper, if it's silver, we call it tarnishing, but it is actually the same exact thing. Okay? It is metal reacting with oxygen in the air. Okay? They will also react with acids. Acids will break apart metals. It will break them down. Questions? Okay. So now if we put the word non in front of something, or it's not really a word, it's a prefix. If we put the prefix non in front of something, what does it mean?
No.
Not. So a non-metal is actually the opposite of a metal. Okay? And those are the ones that are up there in that upper right-hand corner. Okay? Properties, physical properties of a non-metal. They're dull in appearance, meaning they are not shiny. What does it mean to be brittle?
Fall apart easier.
Thank you. So, for example, I hate 0.5 mechanical pencils. Why?
Because your lead is so small.
They're brittle.
They're brittle. The first of all, it's not lead in there. What actually is it? Graphite. Anybody know what graphite actually is? What? Oh. It's an element on the periodic table. Graphite, ladies and gentlemen, is carbon. It's carbon. That's all it is. And when you write, you leave behind the carbon on your mark. Think about this. Charcoal is actually burnt up what? Charcoal, the part that remains, mostly carbon. Guess what you could do with a piece of charcoal? Write on a piece of paper with it. It will leave a mark behind.
Wow.
Okay? Now, the reason I hate 0.5 is because when I write, I always break the stupid lead. Always. Always. So I have to get at least 0.7 or higher. Otherwise, I'm just writing, click, snap, 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 constantly.
Because I go mechanical.
Because non-metals are brittle. They're meant to cut. The graphite in your pencil is meant to fall apart. Don't get me wrong. Otherwise, it wouldn't leave a mark on your paper. Okay? But it is so brittle, to me at least, that I don't like the very thin stuff. Okay? I don't like the very thin stuff. They have a low density. That means there are not a lot of atoms packed into a lot of space. Well, think about it. What state of matter are a lot of the nonmetals in? Not all, but a lot of them. Look above your head. Periodic table above your head. A lot of the nonmetals are what color on that periodic table? The nonmetals?
Oh, red.
Red. What does red mean?
They're gas.
Red means they're a gas. Now think about it. By nature, gases spread out and take up a lot of space. Not a lot of particles in those spaces. Low density. Low density. Okay? And again, they're gases at room temperature. They are non-conductive. Meaning, if conductive means it can easily pass through, what does non-conductive mean? It doesn't easily pass through. With electricity and with heat. How does this list compare to your last one?
It's the opposite.
Thank you. They are the exact opposites of each other, ladies and gentlemen. So, do you really need to remember both lists? No. Just remember that whatever the properties of a metal are, non-metal are pretty much the opposite. Non-metals are pretty much the opposite. Okay? Now, non-metals have some chemical properties as well, ladies and gentlemen. Okay? They have some chemical properties as well. They gain electrons. Don't lose, they gain. They form negative ions. So by gaining electrons, by taking electrons, by the way, where do they get the electrons from?
Nucleus.
Where would a non-metal get electrons from? A metal. Metals are trying to get rid of them. Non-metals say, yeah, I'll take them. They become negative ions. Chemical properties, non-metals react with hydrogen. They react with oxygen. They react with, or they do not react with, sorry, I got ahead of myself there. What do you think they don't react with? Think about it. What? Acids. Okay. Some nonmetals will still react with water. But remember, metals reacted with acids. Nonmetals don't. Why? Because they're what of each other? They're opposites of each other. They're opposites of each other. Okay. Sorry. Is everybody finished? I keep switching it on you. Anyone need more time? Okay. So, ladies and gentlemen, my question for you, based on what we learned earlier, based on what we said a little while ago with the reactivity of the elements, what is the most reactive metal on the periodic table? Now, think about where it would be. Think about what happened with reactivity in our demonstration. Where would the most reactive metal on the periodic table be? Lower what?
One of the lower periods.
Okay, why?
Every time you go down, it's going back.
Thank you. Very good. So we're using some logic now. Very good, Alex. When you go down the periodic table, they become more reactive. So the most reactive metal would have to be somewhere at the bottom, correct? So now you got two choices. Bottom right, bottom left. The one thing that wouldn't happen is it wouldn't be somewhere in the middle. That wouldn't make sense because that wouldn't be a pattern, correct? It would have to go up and then down, right? Doesn't do that. So where is the most reactive metal? Francium, right here in the lower right-hand corner, ladies and gentlemen. I'm sorry, lower left-hand corner, my bad. This is the most reactive metal, ladies and gentlemen. Francium is the most reactive metal. Okay? How reactive a metal is when reacting with similar substances. That's how we measure reactivity. That's why we put what with all of our metals yesterday? Water. Wouldn't be fair to use the different substance because maybe that's what's causing it to be more reactive. So we do it all with these similar substances. And as you move across a period, what happened to the reactivity? We talked about this carefully. Sodium to magnesium to aluminum. As we're moving across, what is happening to reactivity? It is decreasing. Okay? It is decreasing. Okay? So again, sodium, very reactive. Magnesium, not very reactive. Aluminum, not reactive with water. That's decreasing. But then when you move down the periodic table, what happens? It increases. It increases. Therefore, ladies and gentlemen, the most reactive metal would be the one that is furthest to the left and furthest down. That, ladies and gentlemen, is francium. Okay? Now again, people ask, well, why couldn't we see what happened with francium? Why? What? No, you could safely react it with something very far away. But what have I told you about francium before? It is about $1 billion a gram. Very expensive. And it has a half-life of 22.5 minutes, so even if you have some francium, it ain't going to last long. Okay?
How do they keep it going?
They can't. Actually, they have to synthesize it in the lab to make any large quantity. And I mean, a couple of grams of it is considered a large quantity. Okay? So, Francium is the most reactive metal. Okay? Now, please think about this. Iron, nickel. Which one is more reactive, iron or nickel?
Nickel.
Why?
Because it's farther to the right.
Okay, but what did you tell me as we go further to the right?
It decreases.
So which one is more reactive, iron or nickel? Iron. Which is more reactive, tungsten or gold?
Tungsten.
Why?
Just run it to the left.
Further to the left. Or here's what I tell people. Which of these two is closer to here? Tungsten or gold? Tungsten. So again, there's nothing wrong with what you're saying. Further to the left means more reactive. What I will tell you is the closer you get to this, the more reactive you become. So all right, manganese or tectinium? Which one is more reactive? Manganese or tectinium? Why? Because it's further down or closer to francium. Calcium or strontium? Calcium or strontium?
Strontium.
Further down, strontium is going to be more reactive. Strontium or barium? Barium. Potassium or cesium? Cesium. So as a general rule, if we're going to say this is the most reactive metal, the closer you get to it, the more reactive you will become. Now, the one thing I will not do to you is something like this. Which is more reactive, potassium or barium? Why barium? Well, it is further down. Why would you say potassium? Because it's further to the left, and that's a more reactive family. To be honest, we can't know for sure. My guess would be potassium. But again, I won't ask you to compare things that either aren't in the same family or the same period. These were in the same family. These, same period. That's all I will ask you to do. Okay? All right. So, what did we say about nonmetals again? They were the what of metals? Opposite. Okay? So somebody tell me, where is the most reactive, or what on the periodic table is the most reactive nonmetal, and why? Okay, so what would it be? Helium? Well, Alex, lower left was the most reactive metal. So you're saying the upper right, helium, is the most reactive nonmetal. Do you agree with him? Yes? No? Maybe so. Mariana? Yes? Faith?
I don't know.
So then what's your answer?
I don't know.
Well, if you had to make a guess, what would your guess be?
Well, since francium is on the far left and I guess less effective, the metals I feel like would be the same. As weight. As weight
What?
too. The non-metal. Oh wait.
Well, remember, Alex reminded us of something that we learned just a minute ago. The properties of nonmetals are what compared to metals? Metals are shiny. Nonmetals are? No.
Little.
Shiny. Nonmetals are?
Not shiny.
Dull.
No.
Metals are malleable. Nonmetals are?
Little.
Brittle. Non-malleable, yes, but brittle is the term we use. Metals have high density. Nonmetals have low density. The most reactive metal is in the lower left-hand corner. The most reactive nonmetal, Alex says, is in the upper right-hand corner. Mariana agreed. Do you agree? Okay. Jennifer, do you agree? Yes? Kiana, do you agree? Yeah. Ethan?
Yes.
Christian? Christopher? Yes? Your thinking is 100% absolutely correct. Except for one thing. What family is this?
The noble gases.
The what?
Noble gas.
What's special about the noble gases, ladies and gentlemen? Very good. So what does that mean?
They would react.
Okay, so they don't react. So is it possible for helium, which is a nonmetal, you are absolutely correct, to be the most reactive nonmetal? No, it is not. So now,
Maybe 1 over. So fluorine.
you got it. Your thinking was absolutely correct. Using basic, simple logic. This corner is the most reactive metal. The opposite corner should be the most reactive nonmetal. The only problem, ladies and gentlemen, is we have to take the noble gases out. You cannot talk about the noble gases in a reactivity trend. They're not reactive. So your thinking was correct. So fluorine, ladies and gentlemen, is the most reactive nonmetal, which means as we go across the periodic table, for metal reactivity, it decreased. For nonmetal reactivity, it does what? Increases. What about as you go down a family? It decreases. Why? Because it increased for a metal. All of these are opposites. But remember, we can't go into the noble gases, so the most reactive nonmetal? Fluorine. Fluorine is the most reactive nonmetal. Alex, you were right on. It's just we forgot about that one family that doesn't do what it's supposed to do, or doesn't do what we are thinking it would. Okay? So again, ladies and gentlemen, phosphorus or chlorine, which one is more reactive nonmetal? Phosphorus or chlorine? Which one is the more reactive nonmetal, Helen? Phosphorus or chlorine? What's that? Chlorine is the more reactive nonmetal. Selenium or sulfur, which is the more reactive nonmetal, Jennifer? Selenium or sulfur? Sulfur. It's higher up, it's closer to fluorine. Chlorine is closer to fluorine than phosphorus. So again, as we get closer to that more reactive one, that is a good thing to do. Now, on your periodic table, ladies and gentlemen, if I were you, down by francium, in that spot, I would put most reactive metal by francium. I would write it right on the periodic table. And up by fluorine, I would put an arrow to fluorine, and I would put the most reactive nonmetal, just so that you know where they are. Just so that you know where they are, ladies and gentlemen. The most reactive metal is francium. The most reactive nonmetal is fluorine. So, again, ladies and gentlemen, that will be very helpful for you in this unit. Questions? Oop. Hang on, I'm trying to find it for you. Francium, most reactive metal. Fluorine, most reactive nonmetal. All right, one last slide for today, ladies and gentlemen, and then that will be it. We did talk about this a minute ago. Kiana gave us some help with the definitions here. A physical property, ladies and gentlemen, just as a reminder, we have been through these. We have defined these. I'm just reminding you of the definitions. Is a property that can be observed without changing a substance. Examples: mass, volume, color, texture, boiling point, density. Now, again, if you're sitting there going, wait a minute, don't you change the substance when you boil it? You change the state of matter. You do not change what is there. Water is still water after it is boiled. Water is still H2O even when it is frozen. Doesn't change the chemical makeup of it. Changes the state, yes, but not what is actually there. Okay? Chemical property is a property that describes how matter reacts. Chemical properties are things like, can it rust? Can it oxidize? Can it tarnish? Is it corrosive? Is it flammable? Those are chemical properties. How will it change? Okay? A physical change is a change in which no new substance is created. Now, if you'll notice the definitions here, a property that can be observed without changing the substance and a change in which no new substance is created. Please remember, these are like predictions. These are what? If it is a change, it is a what? What's another word for a change? No. A change is an action. It is something that is actually happening. So, being able to burn is different than being burning. Being able to burn is a property. Burning is a change. Okay? A chemical change is a change in which a new substance is created. Again, these are actions. These are things that are happening. These are things that can happen, that will happen under the right conditions. Questions? Okay. What are some signs of a chemical change again, ladies and gentlemen? We've been through this once, but what are they again? We look for a gas to be released. We look for an unexpected color change. Change in energy. And finally, a precipitate forms, a solid that settles out of solution. Those are signs of a chemical change. Questions, ladies and gentlemen?